Hello, we're talking about some bonding theories. And the first bonding theory that we want to look at is called valence bond theory, or VBT. Remember that a bond will ultimately have two electrons. And we're talking about covalent bonding, which involves a sharing of electrons. In valence bond theory, we're going to talk about how the valence electrons come together by the overlap of atomic orbitals. And this gives rise to the formation of a bond. So it's the overlap of atomic orbitals that makes our bond. The simplest example is to look at diatomic molecular hydrogen, H2. Remember, hydrogen has a ground state electronic configuration of 1s1. So if we have a couple of hydrogen atoms, their 1s orbitals, remember they're spherical, come together, they can overlap those atomic orbitals, and that would give rise to a bond. It's a particular type of bond that we'll later call a sigma bond. A sigma bond is simply a bond where the overlap lies directly along the internuclear axis. It's just a fancy way of saying that the overlap lies directly between the two nuclei of the atoms coming together to make a bond. Let's look at another example. Let's look at hydrogen fluoride. Hydrogen's 1s1. The fluorine comes from 1s2, 2s2, 2p5 as its ground state electronic configuration. So we've got those 7 valence electrons, and we're going to be interested in looking at the 2p electrons. So here's my hydrogen with his 1s orbital. Here's my fluorine. He's got this trio of 2p orbitals. Remember, these p orbitals, they have 2 lobes to them. So they're not 6 orbitals here. They're actually 3 orbitals. And they're not flat. They're arranged in 3-dimensional space. So you got 2px, 2py, 2pz along the 3 Cartesian coordinate axis. So as these 2 atoms come together, what we're going to do is we're going to see the overlap of the 1s orbital from hydrogen with one of the 2p orbitals from fluorine. And so that overlap is going to give rise to our sigma bond. So how do we explain why these bonds are happening? The formation of the bond results in a lower energy for the system. So we could do a plot of the atoms as they come together. We could have potential energy along our y-axis and our internuclear distance along our x-axis. If the nuclei are too close together, we've got the repulsive forces of the nuclei. If they're too far apart, there's not going to be a bond that's formed. And so there's this optimum distance the overlap. And so, down here we'd have the two of them overlapping way too much. The nuclei are pulsing each other. And out here, there's so little. There's no overlap. And so somewhere in the middle, there's this optimum overlap that we have where that minimum energy takes place. So why don't we use valence bond theory to explain all of our bonding? Well, let's look at a molecule like CH4, methane. We've got hydrogen with its 1s, 1 ground state electronic configuration. Carbon's 1s2, 2s2, 2p2. It's got 4 valence electrons. And so that overlap, we got carbon, and if we've got this trio of 2p orbitals that we want to somehow overlap with hydrogens, a simplistic way of looking at this is if we can overlap a 1s orbital with a 2p orbital, there are only 3 available 2p orbitals for us to overlap, for there to be sharing of electrons. And so how are we going to put in that 4th atom? So that sort of becomes a quandary to us. The other thing is, if we're really truly 2p orbitals, those bond angles are all 90 degrees to one another. And even though this Lewis structure sort of intimates that the bond angle might be 90 degrees, we know the Lewis structure only shows how those electrons are arranged and obeying the rules for writing Lewis structures. So they don't necessarily show what the true electron or molecular geometry is. And there are 4 electron domains around that carbon. That carbon is really tetrahedral. And so this is where valence bond theory starts to fall down. And this is where we need to look at some other bonding theories that might better explain these higher orders of bonding in molecules that we'll be looking at.